All right, in this section, we're going to take a look at 3x3 systems of equations. So 3 equations, 3 unknowns. So far, we've been solving these 2x2 systems, and we have these 3, techniques to solve them. And those algebraic techniques, substitution and elimination by addition, you can make those work for a 3x3, although it's pretty labor intensive. So Cramer's rule is definitely the preferred way to solve a 3x3 system for us. Again, you want to make sure that your system is written in standard form. So we've got all of our x's lined up, all of our y's, and now z's. We have a third variable, and then the constants by themselves. And we model or represent this system of equations with a matrix, with an augmented matrix, just like we would do with the 2x2 system. So that should kind of be in keeping with what we might expect to see. And if we're solving this system with Cramer's rule, again, you will make sure it's written in standard form. You write the matrix that represents them, and then use Cramer's rule. Now, rather than list the, A1, A2, A3, and all of these, which can look pretty messy and just end up staring into this sea of subscripts, I just want to kind of describe how we make these matrices. So first of all, you'll notice we're finding the determinant of the coefficient matrix for the denominator, just like we did with the 2x2 systems. That doesn't change. And then the matrix that we get, that we're going to use up top, we obtain in the same way that we did with the 2x2 system. If I'm solving for x, I'm going to replace the x column with the constant column, and the y and z columns stay the same. If I'm solving for y, I'm going to replace the y column with a constant column, and the x and z columns stay the same. And then likewise, if I'm solving for z. We're going to do an example. Now, the example we're going to do here is an example of one that takes probably the most amount of work. I mean, at worst, you're going to have to put in this much work to solve a 3x3 system using Cramer's rule. And the way I can tell that this is going to be one that requires a bit of work is because there's no zeros. You might recall when we were learning about matrices and how to find the determinant of a 3x3 matrix that we really wanted to take advantage of zeros because that would make finding the determinant easier. And there are no zeros anywhere in this system of equations. So at worst, when you do a problem, we'll have to do about this much work that we're about to dive into for example 422. So when I solve a system of equations using Cramer's rule, the first thing is represent it with an augmented matrix. So I'm going to write that just right next door. It's already in standard form, so I got my x column, 3, 2, 5. I got my y column, 2, -3, -2. And I got my z column, -5, -1, 7. My constant column over here, -1, 11, 9. Now, rather than put the matrices and find the determinants inside fractions, I'm going to just compute the determinants that I need. And I'm going to try to do this, even though it'll be a little bit labor intensive, I'm going to do this using the least amount of work possible. So first, I'm going to just compute determinants I need, and I know that for all of them, I'm going to need the determinant of the coefficient matrix. So because that's going to be the denominator for all of my solutions. Now I can expand on any row or column that I want. I'm going to just sort of jot down the system or the pattern of signs here. So I'm going to go ahead and just expand on the first row. There's no like advantage, I suppose, to using one row over another row because I got no zeros. If I had zeros, I'd want to make sure I took advantage of that. But I'm just going to use the first row here. So I'm going to have 3 times the determinant of, let's see, the 2 by 2 I get when I eliminate that row and column. That would be -3, -1, -2, 7. And then minus, again, I'm just sort of using that pattern of signs, minus, and then I take this value 2, and then the determinant of the 2 by 2 that I get, let's see, the 2 by 2 I get if I eliminate that row and column is 2, -1, 5, 7, and then plus, that's a plus, because that's a plus, -5 times, let's see, if I eliminate that row and column, I am left with 2, -3, 5, -2. Okay, so now let's evaluate. I've got 3 times, and then the determinant of this 2 by 2, 3 times 7, -3 times 7 is -21, minus a +2, minus 2 times, let's see, 14, minus a -5, that'll be a +5, minus 5 times -4, minus a -15, so that's +15. So 3 times -23, or sorry, yes, -23, minus 2 times 19, minus 5 times 11. Minus 5 times 11. So I got -162. Okay, so we've got that determinant. And now what we're going to do, you know, just to not maximize the number of determinants I have to find, we only need to find 2 more determinants. I'm going to find the determinant that will let me solve for x, and I'm going to find the determinant that will let me solve for y. And then once I know the values of x and y, I'm going to substitute them into one of the equations to find x. And that way I only need to find 2 more determinants instead of 3. So let's get the numerator for x. So I'm going to replace the x column with the constants -1, 11, 9, and then the y and z columns stay the same. Okay, again, and I think I'm just going to use the first row. It's as good as any other. So I've got a -1 times, let's see, that'll be -3, -1, -2, 7, and then minus 2 times, let's see, 11, -1, 9, 7, plus -5 times 11, -3, 9, -2. Okay, so that's -21 minus 2. Minus 2 times 77 minus a -9, so +9, and then minus 5 times -22 minus a negative 27, so plus 27. Let's see, negative 23. That's 2 times 77 plus 9 is 86. And the negative 22 plus 27 is 5. Okay, so we got 23 minus 2 times 86 minus 25. Get negative 174. Okay, so now one more determinant to find. We'll find the determinant that we need to solve for y. So let's see, our numerator for y. The x and z columns stay the same, so my x column was 325. My y column I'm going to replace with a constant, so negative 1, 11, 9. My z column stays the same. Alright, so our first entry, 3 times this 2 by 2 that we get is 11, negative 1, 9, 7. Minus a negative 1 times 2, negative 1, 5, 7. And then plus negative 5. And that 2 by 2 that we're left with is 2, 11, 5, 9. Okay, now let's whip into a frenzy of multiplying and subtracting. Let's see, 77 minus a negative 9, so plus 9. Then we have plus 1 times, let's see, 14, plus 5. And then minus 5 times 18 minus 55. 77 plus 9 is 86. Plus 19 minus 5 times 18 minus 55 is negative 37. Okay. Alright, let's see what we got here. 3 times 86. Plus 19 minus 5 times a negative 37. 462. Alright, so we've got all the determinants that we're going to need to find here. For our value for x, let's see, that numerator was negative 174, and the coefficient matrix, that determinant, which is everyone's denominator, that's a negative 162. So x is negative 174 over negative 162, and we can approximate it, or we can get a reduced fraction. Hit the math button, and the first option is convert to a fraction, and that's 29 over 27. The value for y, that'll be 462 over negative 162, and we could find that as a reduced fraction. Negative 77 over 27. And now we just need the value for z, but we know x and y, so we can use one of these equations to solve for z. So the second equation in the system looks like this. 2x minus 3y minus z equals 11. And I'm picking the second equation because I think it'll just make it simpler. So if I add z to both sides and subtract 11, we get z equals 2x minus 3y minus 11. So now I'll just plug in the values I have and throw them in the calculator. So 2 times 29 over 27 minus 3 times negative 77 over 27 minus 11. So we get that value there. And something seems off. Hold on. So let me try that again. 2 times 29 over 27 minus 3 times negative 77 over 27 minus 11. Oh, that looks better. Let's see. Okay, so we get negative 8 over 27. Alright, so our solutions are this sort of triplet of values here. So again, like I said in the beginning of this example, this problem represents, probably the most work that we'll need to do when we're solving a 3 by 3, just because there were no zeros in the system. At worst, it'll take this much work. A lot of times it'll be a little bit less work because we can take advantage of any zeros that might appear and make our determinants a little bit easier to find. Let's finish up with a nice word problem. We're going to write a system of equations that represents this problem. And then we can solve that system using Cramer's rule. So a person invests $15,000. Some of it's at 5%, and another chunk of it is at 5.5%, and the rest of it is at 6%. And then the total annual interest is $850. Then they tell us that the amount invested at 5.5% is 3 times the amount invested at 5%. So we want to know how much is invested at each rate. So there's a lump sum. We've got this chunk of $15,000, but we're kind of splitting that up into 3 chunks. So we can let X be the amount invested at 5%. Y can be the amount that is invested at 5.5%. And Z can be the amount invested at 6%. So we have 3 unknowns. That means we want to write 3 equations. So one equation is pretty simple, and we get that just from this first part here. A person invests $15,000. That means that if I add up the X, Y, and Z all together, that's going to make $15,000. All right. Now, the next part is that the total annual interest is $850. That means if I add up the interest earned on each of these chunks of money, that's going to add up to $850. So 5%, X is invested at 5%, so 5% of X, that's 0.05X, plus the amount I get from those Y dollars, that's invested at 5.5%, so that's 0.055y. And then the Z dollars is invested at 6%, so that's 0.06Z, 6% of Z, and that all has to add up to 850. And then the last bit here, it says the amount invested at 5.5% equals 3 times the amount invested at 5%. So I'm going to kind of go off to the side here and write that equation before I get it in standard form. So the amount invested at 5.5%, that's y, is 3 times the amount invested at 5%, is 3 times x. So if I were to like subtract y from both sides, we get 0 equals 3x minus y, or 3x minus y is 0. So I'm going to write that equation now in standard form. And we have no z's here, so I'm actually going to write 0z. And I like to include that term because that's a little reminder that I'm going to have a 0 in that row in the matrix. So here's the system. Let's write the matrix. 1.05, 3, 1.055, negative 1, and 1.060. And let's see, on the other side we got 15,000, 850, and 0. Alright, so we know that we're going to need to find the determinant of this coefficient matrix. So let's begin with that. Alright, so as we've mentioned before, I want to take advantage of any zeros if I can, so I'm going to expand on the bottom row. I'm going to write out the system of signs here. Alright, so it's another plus minus plus row, just like the top row. So that determinant is 3 times, let's see, that 2 by 2 that we get when we eliminate that row and column, 1.055, 1.06, minus 1 times, that 2 by 2 that we get is 1.05 and 1.06. And then plus 0 times, and now we don't care what's in that matrix because we're multiplying it by 0. Alright, so let's find this determinant. Let's see, 1 times 0.06, 1 times 0.055, 1 times 0.06, 1 times 0.05, and that's 0.005 minus 0.01. We get 0.005. Okay. Oh, you know what? Hold on a second. So we have this, we grab the 3, that goes there, and then we need to subtract the negative 1 times this. So that'll end up being a plus, which follows us down here. So let me try this again. Okay, 0.025. Better. All right, now let's think about our strategy here, right? So we found the determinant of the coefficient matrix. We would need that regardless. Now let's think about what we want to solve for first. So, you know, when we're making the determinant that we need to find to get the numerator for x or y or z, you know, we replace that column with the constant column. So notice we have another 0 in that constant column, and that's great, which means I'm just going to choose anything but z. If I put it in the z column, I retain a 0, and that's nice. But if I put it in either the x or the y column, then I have 2 zeros in the same row, and that's going to make it way easier. So let's I'm going to just solve for x. Let's get the numerator for x. So the x column, I'm going to replace that with the constants. It's 15,850 and 0. And then the y and the z columns stay the same. So 1.055, -1, and then 1.060. And of course, I'm going to pick that third row. I've got 2 zeros. So when we find that determinant and expand by cofactors, I start out with 0 times, you know, who cares what that determinant is, minus a -1 times the determinant of, let's see, what do we get when we eliminate that row and column? $15,000 or 15,850, and then the last column 1.06. Let me make this not so cramped. And then plus 0 times, again, you know, who cares what that determinant is. So it's just the middle one that I need. So there's a 1 times 15,000 times 0.06. So that's 900 minus 850. And that will give us 50. So now we know enough to solve for x. Let's find x. We know that x is 50 divided by 0.025. So we get 2,000. So that's $2,000 invested at 5%. Now we actually don't need to find any more determinants, because if you look at our system of equations, here I know the value of x. This last equation just relates x in terms of y, and in fact, maybe it even makes more sense to use this form of the equation first, right? Y is equal to 3 times x. So there's how we can get y. So that's $6,000. Invested at 5.5%. And then I can use either of the other two equations to get z. I think it makes the most sense. It's easiest to use the first equation. We know that all three amounts add up to 15,000. So that means that z is 15,000 minus x minus y. So minus 2,000 minus 6,000, and we get 7,000 at 6%. All right, so here's an example of, we had to model a problem with a system of equations, but here's an example of a system where we really got to be pretty efficient in how we solved it with Cramer's rule. We had some zeros we could take advantage of and make those determinants easier to find, and even only had to find the values of 2 determinants instead of 3, like in the last one.